living creatures, with all that energy being used, particularly in the metropolitan areas here in the United States, in India, Japan, China, and if I turn your head here, look at all of Europe. Empty is the Amazon region at the bottom here, and the Sahara Desert, and some of the deserts also in Northern Asia in general. So it's a matter of interest that we all share together in terms of energy in general. The way we are going to conduct our meetings together is that I'll try to share the screen and combine the sharing of the screen with a lecturing, giving a lecture. And to be able to access our website, you got to that link right here. It's under mragheb.com. If you open up that link, and I appreciate if you keep it on your best. I don't know what happened here. Okay, here we are again. Let me do some adjustments in the screen here. This is basically our website, and it's a site that is somehow more like global or than it is local. And the site is available for people from, we counted with the ABET people visiting us, about 45 countries really access our site. So if you go to that link here, you'll see that the latest is that we are being accessed on our site from people from India, United States, Egypt, Pakistan, and Russia. So it's a global kind of effort. It's a public service from the University of Illinois that we are reaching to the whole world. Same as MIT. However, in our case, as you will see, we try to provide a complete full lectures and notes for the material that we cover in the class. At MIT, they have a mandate to have PowerPoint presentations, which is what I would call shallow learning. When you read the material either on our website, or you go to the web pages or books or at the library, then that is what's considered in the field of artificial intelligence as deep knowledge. So we are better, we should be proud of it, that we are basically considering deep knowledge rather than shallow knowledge. And this is another list of the visitors. I have a typo here by a country. You could see here total visitors, United States, Taiwan, and if you count them, I think it's Greece even, Ghana, India, Australia, Romania at random, Morocco. This is the access to our website. So you're in a company of students and people who are interested in the topic that we are covering, nuclear power engineering from all over the world. This is a portal to our class. You could see here already for the next semester, the same class that we are going to take as a crash course here, 2 hours, 2 consecutive hours, maybe with some 10 minutes rest in between. Next semester will be taught face-to-face, and it will be at the campus instructional facility to still maintain some kind of distancing in the lectures. The next semester also I'll be teaching the course on the safety analysis of nuclear reactor systems. Same, you can access it there. You can just read it for the fun of it if you want. The last semester, we taught a pioneering course on energy storage engineering. We also taught another pioneering course on wind power systems. This shows you that the interest that I'm reflecting here is the interest in both nuclear energy as a future energy source for the whole world, as well as the renewables in general. But to achieve the concept, the introduction of renewables, since they are intermittent, energy storage becomes extremely important. You can also access lecture notes on some of my other interests on Monte Carlo simulations in engineering. I have a complete set of notes there if you want to learn about Monte Carlo simulations, fuzzy logic and its applications, which is the possibility theory rather than the other field of probability theory that is taught in other contexts here. My interest also lies in nuclear radiological safety and the principles of radiation protection. If you want to read some material that I have published in my blog here, it's not part of the courses. You find that you can learn about societal risks in general. That's also part of the safety course, and maybe find ways of protecting yourself and surviving our pandemic right now. This is some material that is ready to maybe be published as a paper, but not published yet. And then you can find down some select publications. Many of our lecture notes have been invited by book editors to be published as book chapters. For instance, here the nuclear naval propulsion is a unique chapter from our notes that has been published as a chapter in a book, as you could see here. And basically, it's being taught to cadets in military schools over the summer. We welcome that. You'll find some journal papers here on fusion, fission hybrids, my interest in fusion as well as fission, the restoration of the global equatorial current, and using nuclear excavation, which is has a name as nuclear civil engineering for our civil engineers, neutron disintegration in condensed media. You'll find really a large number, well, there are some articles which are not really technical papers. Some people even publish videos from conferences. You'll find lots of conference papers with students, as well as a very large number of technical reports that you can explore. I invite you to explore those technical reports just for the fun of it. If we go back here, this is the portal for the courses I teach. We go to our own portal. This is the course that we are teaching this semester. It's designated as NPRE 402. You know that already since you registered for it. And you'll find that we have a complete set of notes. And you could see the links to the notes here. Different parts, the dawn of the nuclear age, modern nuclear science. There are parts on fusion energy, radioactive processes, fission, fusion, space nuclear power for our wonderful space engineers. Then we get into the theory on how to get nuclear reactors to operate. And in that case, your group of students becomes privy to the secret of the nuclear age. So you become an elite group of engineers learning that process. Radiological science is the protection against the effects of radiation and using radiation for beneficial purposes like in nuclear medicine. Some of you may be interested in pursuing graduate studies, maybe in nuclear medicine and radiological engineering. The nuclear safety is briefly considered here because it has a course by itself. And you have lots of interesting applications, among them, for instance, the ideas of nuclear marine propulsion that I mentioned to you. We have also some internal links. For instance, you can go to group cross sections that you could use maybe in some of our calculations later on and solving the problem. Along this line, we have, after you are expected, of course, to read the material in the lectures, we would have a teaching assistant helping us. She's already joining us right now. And so you access that link. That link will be updated. We have only one TA, the first one for this class this semester. The others have helped in the previous semester. And then each lecture would be accompanied with a an assignment. And in that case, the assignment helps in understanding and accessing the information in the class. I have it in two formats, one in the PDF format, so you can access it on your phone maybe, and or you can have it in the form of a Word file. This is a tentative form of the assignment for today. I'll change that a little bit. So you'll have a reading assignment. You read the preface that we are trying to cover today, and then you'd have a written assignment, and you turn in that written assignment to the Compass 2G to the TAs that who would be helping us. The assignment, each lecture would have an assignment, and it will be due 1 week from the day it is assigned. So today is the 14th. Your assignment is due on or before the 21st. We'll give you a week to work on the assignment. Somebody would ask, oh, do we need to read the lecture note chapters? By all means, those lecture notes are there to be read, and the assignments are there to encourage you to read the notes, and you'll find the answers to the assignments in the notes. And you'll have access to the TAs, of course, access them by email. If they give you their phone, that's their prerogative. And please, we ask you to submit your assignments to the Compass 2G Illinois. The tests are going to be not submitted to Compass 2, they'll be submitted to me personally because I grade the tests. And in terms of tests, we have 3 tests, 2 midterms and 1 final. I'll come back to how the grading is going to be conducted. In case of internet rationing, like overwhelming Zoom, like sometimes you get interruptions on the internet. Last week, for instance, there were quite a few interruptions. Then in that case, we switch the mode to only accessing the lecture notes, turning in the assignments, and we will not be able to do the Zoom meetings. If there is an interruption of the process of the Zoom meetings, or for any kind of situations like maybe the pandemic having another wave, then whatever assignments and whatever tests have been taken will be used for the final grade. So please be aware on the website of the list of assignments as well as the access to the TAs. Over the semester, we'll have 2 midterms and 1 final. That would be first midterm, second midterm. It would be added as a link right here. Each one of the tests will get 20% of the final grades, and the assignments will take 40% of the grade. We are going to take an attendance for extra credit points, so please try to attend all the Zoom meetings. I haven't yet set up the first midterm or the second midterm or the final, but basically all I know about the calendar so far is that we start instruction today, and the instruction ends for your planning on August the 5th. Today, our interest would be to look at energy in general as a preface. And so these are basically the rules of the game. I'll stop sharing and see if you have any questions. If you have questions, please add them on the chat room where we can communicate in that case. Energy available, and many of you will have fun basically reading the material sitting on the beach, I hope. No more questions. I'll go and share the screen again. And I'll minimize everything other than the screen. And we are going to start here as a preface. The preface is going to be a general view of what we are trying to do. Definitely our interest is nuclear phenomena in general, plasma physics maybe a little bit, and radiation science. The title describes it, and it is in the form of a textbook that is completely on the web in general. And the material, of course, is to be read, but we go back a little in history about how nuclear energy is prominent today. Remember that in your other classes, you have been taught and you have been very well informed about the forces of nature. Like the current state of knowledge is that at the time of what is described as a Big Bang, 13.7 billion years ago, the forces of nature were combined together. So we had the gravitational force, we had the electromagnetic force, we had the weak force and the strong force all combined. And supposedly, according to theory at least, these forces separated. Now, the strong force is a force that keeps the nuclei together, and that energy, if released, is released in the form of what we call fission energy or fusion energy. The mass and energy gets transformed according to the famous Einstein equation. So this is something that we are going to cover in our class. The weak force described primarily the process of radioactivity, and radioactivity is another force of nature that happens on a weaker scale than the strong force that keeps the nuclei together. So you find radiation emitted from different nuclei, isotopes in particular, of the different elements, and we'll cover also that in our class. And then we have the electromagnetic force that accompanies the process of the weak force in the emission of X-rays and radiation from the nuclei. And so in our class, we try to cover the three forces out of the four forces of nature. We leave part of the electromagnetic spectrum in the region of microwaves and radio waves to other classes in electrical engineering or computer science or chemical engineering. But we cover in three of the forces of nature, and imagine you're graduating without being well learned in the process. We argue that the world in our future is going to be depleted in the hydrocarbon sources of energy that we use today. I'll make that argument today. It is not just a matter of modifying the climate, and that was the issue of concern before the pandemic, which took over our main concern. Basically, we have to worry not just about climatic change from the burning of fossil fuels, but we also have to worry about their depletion. The different hydrocarbon sources, natural gas, petroleum, and coal, are energy that is stored from a nuclear reaction. The nuclear reaction is the reaction in our star, the sun. And that energy has been stored in what we have as coal now and petroleum, and both of them come in from dead animals and plants, coal from plants and dead plants, and petroleum from dead animals that happened basically in our oceans. So over 200 million years, that solar energy or nuclear energy, fusion energy from the sun has been stored there over 200 million years. And in our current civilization, over 200 years only, we are using that stored energy. At some point, we have to worry about having it depleted. And in that case, it would be the end of our technological society. So the only alternative available to us is to switch to a system of energy production and use that uses renewables, solar energy, wind energy, hydroelectric energy, and of course, nuclear energy is the most concentrated or high energy density or high specific energy form of energy that is available to us to continue our technological civilization. The application of nuclear energy, unfortunately, started in an aggressive way with at the end of the Second World War in the bombings of Hiroshima and Nagasaki. And that would have been a very bad or undesirable use of nuclear energy. So many smart people definitely turned the attention into its civilian and pacific uh, peaceful uses of nuclear energy. One of the great persons who did that is one of the best United States presidents shown here, President Eisenhower, Dwight D. Eisenhower, David Eisenhower. And basically he addressed here in that picture the plenary session of the United Nations and on December the 8th, 1953. And basically, I quote him here: "To the making of these fateful decisions, United States pledged before you and therefore before the world its determinations to help solve the fearful atomic dilemma, to devote its entire heart and mind to find a way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life." I think we share all that kind of perception, and we want to learn how to use nuclear energy peacefully. That speech was honored in a way by a stamp issued by the United States, recent stamp showing atoms for peace for the whole world in general. Notice that in terms of civilization, the harnessing of fire as a chemical process, as we know, fire is an interaction between the in the atomic structure, the outer electrons of the carbon atom when it combines, say, with oxygen in the atmosphere. That discovery of fire defines the past and the present of humanity in general. And however, now we also have at our disposal in terms of knowledge, nuclear energy. Both of them, fire and nuclear energy, can be destructive, but their benefits definitely and advantages are indisputably recognized today. Nuclear energy today can be argued to be a safe, clean, and primarily carbon-free, because in that case, we are like a fish in a fish tank. The atmosphere of our Earth is not that thick, and we are really destroying it. So we are destroying our livelihood as well as other forms of life, plants and animals that we are stewards of in general. The unfortunate thing is that a report by the National Science Foundation titled Science and Engineering Indicators suggests basically that 74% of Americans know don't know that the Earth revolves around the sun. Imagine that, the flat earthers thinking that we are living in the flat Earth. In terms of in geological scales, we are some kind of uniquely positioned in between the very, very, very large structures of the universe. You can go from, as humans here, we are in the middle. If you take this as 100 centimeter in height, 1 meter maybe, on our right, you find the bacteria, the viruses, and the molecular structure, the atoms, and even the nuclei. But we also face on, with a larger scale of mountains, the Earth itself, our solar system, and then we have also the universe at large. Sir Martin Rees presents us with that unique position of our human race in the middle of the different dimensions of the universe. A very, very, very small, 10 to the minus 20 centimeter, and the huge, large size of the whole cosmos, 10 to the 25th centimeter in general. Along this line of thinking that we are the basis of a technological society, some other cosmologists, one gentleman, Russian, Kardashev, came up with the Kardashev scale and suggested that different civilizations can be described by the amount of energy that they use. And he has what he calls the type 0, type 1, type 2, and type 3 civilizations in terms of the power that they use, not the energy, but the power that they use. And some other cosmologists came in even with another description of the level of use of power that civilizations use. So you describe civilizations in terms of the power that they use. And the fascinating thing is that humanity has not even reached what is designated as a type 1 civilization. So each one of these levels of civilizations is described by the amount of power that they use. Now, when we define power, let's be careful here. Power is energy per unit time. So in that case, when you take a unit of energy, joule, and you divide joule per second, that is the unit of watt. The inventor of the steam engine is honored by the unit of power. So you find that the type 1 civilization here basically is characterized, according to cosmologists, as using a power level of 10 to the 16th watt. And that's power from their own planet. And for us as humans, we haven't even reached that level yet. We are at the level of 0.75 before reaching that type 1 level of civilization. Type 2 would be when a technological society can reach and basically harness the power in its whole solar system, meaning that we get all the energy from our star, the sun. We are far from that. A third level, that would be type 2 is 10 to the 26 watt. So that's within our star system. Type 3 would be 10 to the 36 watt. That would be using all the power in their galaxy. Type 4 would be 10 to the 46 power watts. That would be in their whole, this would be solar system. This is the galaxy. And then some people even talk about the type 5 energy accessible would equal that. All of the energy accessible in not just our own galaxy, but all the rest of the universe in general. As humanity will sustain its energy needs from dead plants and animals, that's coal and petroleum, we have to move into our future. That's our fate. At some point, we are going to be having to expand life in the rest of the universe. However, if you read more about the topic, you'll find that there are hurdles to be surmounted. And you may have read about the Fermi paradox, or probably add some material about it. Enrico Fermi is one of the pioneers in nuclear energy. Fermi Lab around Chicago is named after him. In in a lunch meeting with his colleagues, he came up with a question: if there are aliens, where are those other civilizations? So that's some kind of a question. It turns out that some cosmologists suggest that for a civilization to proceed from type 0 to 1 to 2, it has to surmount some filters. And in fact, we may be surmounting today one of those filters. The COVID-19 pandemic is a filter that we have to surmount to move into maybe a type 1 civilization. And that is a field of cosmology that you may be interested in reading more about. Let's stay on Earth and think about basically how we use energy on Earth. And if we emphasize the United States, where we have some kind of statistics, you'll find that the statistics are shown by a gentleman, Mr. Sankey, from the Lawrence Livermore National Laboratory. Every year he comes out with a description of the how energy is being used in the United States. And if we consider the use of energy, you'll find on the left-hand side here, there is a listing of the different forms of primary energy, energy that is in a raw shape. We get that energy from many different sources, and then we transform it. We produce electricity primarily, but you can also use it in transportation and get a form of energy that is the useful energy. So you find that energy services here is 31 what? 31 quad. Quad is the unit of energy that is 1 quadrillion. 1 quadrillion is 10 to the 15th watts, and not watts, BTUs. BTU stands for British thermal units. So I'll ask you a question in today's assignment to define the quad. So that is 10 to the 15. Remember, this is a Greek prefix type of notation. When you have 10 to the third, that's mil or 1,000. 10 to the 6, it jumps in 3 orders each time. You find that that is what we call million. 10 to the 6, 10 to the 9th, it's a billion, and 10 to the 12 is a trillion, and 10 to the 14th, 10 to the 15th is a quadrillion. If you go 10 to the 18, that's quintillion. So quintum in Latin is 5. So we jump up by factors of 3 decades or 1,000 at a time. So if we go back to those, these are different Sankey diagrams for different years. You'll find that as of the latest one available, we'll get, this is in 2017, the overall use was 97.7 quads of primary energy on the left-hand side here that the United States used. It didn't differ much in 2018. It increased a little bit to 101.2 quads of energy, which is 10 to the 15th British thermal units. And it went down a little bit in 2019 to 100.2 quad. So whenever I get a new version of that Sankey diagram, I'll keep adding it here. You notice that we are stuck at that 100 almost quad level. The way it is allocated is that we are using most of our energy, at least in 2019, came in from petroleum. 36.7% of our energy came from petroleum. So you know the importance of oil. But remember, petroleum is stored energy from solar radiation, from animals that existed at the bottom of our oceans, and they basically turned into that liquid that we call petroleum. Petroleum is used primarily, as you could see here, into transportation. So 36.7 quads of primary petroleum turns into 8.2 quad of in transportation. In the process of turning that energy, primary energy, into useful products, in that case, energy services, transportation, cars and planes and trains, we are rejecting to the environment a large amount, 67.5 quads of energy. So the overall efficiency of our energy system is at 32.7 divided into 67.5, which is really if you take the total, of course, it's 100. So the efficiency of our energy services is only 33%. So we are having only, we are using our primary energy with an efficiency only of 1/3. And that leaves a huge task for our young engineers and new engineering profession to enhance that efficiency then and having a better use of our primary energy sources. You notice here, petroleum has been the largest source of energy used in the United States, followed by natural gas, 32.1 quad of energy, primary energy, coal 11.4, and the renewable sources are some kind of different numbers of them, but with a very low amounts. Solar energy is only 1 quad. You could see hydroelectric is renewables 2.5, wind 2.7, geothermal 0.2, and biomass 4.9. Nuclear energy in terms of primary energy is 8.46% of our primary energy use. And so you notice here, if you take petroleum, coal and natural gas, this is the most of the energy that we are using today. And this is all depletable. And not only depletable, but of course, these are carbon sources. They are releasing to the atmosphere the carbon that has been fixed into what I call the dead animals and plants. And someday it's not going to be available to us. So what will we have available to us? We'll have the renewables available to us and nuclear energy. And there is a lot to be done in extracting more solar, wind energy. And that is the fate of your generation of scientists and engineers, a combination of those sources, because there's other sources, it can be argued, is not going to be available in our future. So the continuation of civilization depends on having a nuclear future associated with renewables. It's simply simple logic that we can get from that diagram. It's a very important one, obviously. Notice that petroleum is not really used in producing electricity to any great extent. Look, only this little line goes to the electricity generation. So you'll find that we use natural gas, we use coal to produce primarily our electricity, and the electricity goes there for residential uses, definitely commercial uses like factories and businesses, industrial uses, that is the factories. And you notice that petroleum is primarily only used to a little extent to industrial uses, but it's primarily transportation. The important aspect is that the useful energy we get from it is only 1/3 of the total. 32, 33 would be exactly the 1/3 of the total. All right, so this is a situation, the large picture of how energy is being used. Now let's look at petroleum, since it is the primary source of energy in transportation. You'll find that that graph shows us the billion barrels of oil or petroleum. Oil is petroleum. Petroleum stands from Latin as fossil oil, oil that comes from plants in general. And this shows us here the past discoveries of oil wells, like the conventional oil, where you go and drill a hole and then you get a gusher of black oil coming off the ground in Pennsylvania or from Texas. And you could see here that the peak new discoveries peaked in 1960. And we are discovering less and less and less and less more sources of oil. Some people speculate that we may have some future discoveries here. We are here at that point, 2020, much less conventional oil is being discovered. It is substituted for by what is called tight formations oil that uses the process of fracking. It gives us maybe a small peak here in the total energy production. So you could see the total energy production started in the 1930s, and that is not really a long time in terms of historical developments. It peaked around the 1980s, came down, then oil was discovered in Alaska, so it increased the peaking. And within the 2010 and so on, we have the fracking. Fracking is hydraulic fracturing that is squeezing out some more oil, liquid hydrocarbons from different sources. So we are peaking again, even with the new sources from the tight formations of shale oil and natural gas. And in fact, that is not pie in the sky. Some people argue, oh, we can always, with new technology, find new oil. Well, maybe in some region of the world that haven't been explored yet. But look here at the conventional oil in the North Sea, which is by Norway, the Netherlands, and the UK. And it is very obvious that they have reached their peak oil already. So you find that the UK, for instance, is rethinking big time the use of wind power, which is a renewable, and nuclear energy for their future power supplies. Germany has switched big time into also solar photovoltaics, not the thermal solar, thermal solar, thermal solar and thermal and wind power. They have also wind power, but thermal solar has to be close to the equator to be a valid source of energy. This is a peak conventional oil production. It happened already in 1970. This is a conventional oil. Prudhoe Bay is in Alaska, so the discovery of oil in Alaska gave us a new sign of lower peak in oil production. And in 2017, as I told you, the tight oil formation or the fracking type of oil is giving us a new peak, but it's not gonna last. At some point, it will come back again lower. So in a way, we are depleting our resources, and that's what engineers should be and economists should be weary about in terms of the use of energy in general. This is a graph here generated by an interesting scientist here, comparing the different sources of future power that we need. One concern about the use of renewables like wind power and solar energy is that they need a very, very large area of land to extract the energy from the sun. It's really nuclear energy again, but nevertheless, it's a diffuse form of energy. So only nuclear energy, he makes an argument about it, allows us to use a very highly concentrated source of energy. Nuclear energy being concentrated in the mass of matter, initially from fission. And when we use our supplies of uranium and thorium, we'll have unlimited supplies almost in deuterium from the oceans in general. The water that we have in the oceans contains deuterium, the deuterium to hydrogen ratio of 160 parts per million. So our oceans contain a source of energy. And the moon, in fact, the moon, the surface of the moon from the solar wind has also helium-3 nuclei in its, the dust on its surface. So we may be mining the moon for fusion fuel in the future. And that's why we are going to emphasize not just fission energy, but also some material about fusion energy as an energy supply in the future. So in essence, you find that we are using different forms of energy now. And in terms of, it goes against intuition because you hear about Fukushima, and you hear about Chernobyl, and you hear about 3 Mile Island. These are the 3 major accidents that happened in the development of nuclear energy. But in fact, the deaths from nuclear accidents can basically be extremely not even, you cannot even count it. This is the risk or death per terawatt hour. Now, when you take the watts, joules per second, you multiply into hour, you get energy in that case. And terawatt is 10 to the 18th. So in that case, you find that from coal, the deaths from the use of coal, primarily through pollution, because when you pollute the atmosphere, of course, the pollution, the sulfur dioxide, the nitrogen oxides get into the lungs of people and shorten their life. There are also accidents in mining of coal. For instance, coal mines collapse on, and you hear it every year almost, we get an accident where coal miners lose their lives. But you could see here the deaths per unit of energy produced. Again, when you take power, watts, multiply into hours, that's energy, tera energy, you find that coal causes about, let's say, 28 deaths per terawatt hour of energy produced. Petroleum is less in terms of the risk in its use. It leads to less pollution of the atmosphere. Biomass is less. Natural gas is a favored now form of production of energy when it is available to us from tight formations, and nuclear is almost negligible nothing from air pollution, obviously, and from accidents, even with the very serious events that happened at Fukushima. I think it's one or two persons died as a result of the nuclear accident itself. That 20,000 people died from the tsunami that resulted from the earthquake, and we have no control on this. So this is a trend in terms of the use of energy in general. And you could see that coal is being, the use of coal, like when coal power plants are aged 40 years or so, they are being retired in the United States. At least that's the use of energy. And you could see that solar and wind are increasing in their use. So we are on the right track here. We are using the renewables as a replacement of coal. Coal is being retired. Hydroelectric power, when it's available, biomass, petroleum has been increasing, and nuclear has only been increasing by 1%. If you analyze the Sankey diagram, then you discover that petroleum as a supply or a primary energy is primarily using in transportation, as well as natural gas. Industrial, again, it's a reanalysis of the Sankey diagram. It looks like here nuclear and the renewables as forms of primary energy are still a minority. And as we are going to be running out of petroleum, coal, and natural gas, hydrocarbons, this is the only alternative for continuing our civilization. So I can guarantee you that if you have interest in energy, humanity needs you, and you'll have a job on your hands. This is a diagram from NASA that shows us that the Earth is becoming basically a living, almost creature, if you want to call it, and by basically expanding or extending the length of the day. Imagine here North America, Europe, as I said, India, China, Japan, South Africa here, Brazil, South America at night. This is a picture where we are using stored energy from petroleum, as I said, and coal to extend the length of the day, the lights at night. Some other interesting pictures you could see here. This is the Sahara Desert. This is the valley of the Nile. People there are congregated along the Nile and in the area of Palestine and Jordan and maybe Iraq and some parts of Saudi Arabia. So wherever human congregate, you'll find that Israel here, where their energy use is just electrical sources tell you where humans are congregated and using more and more energy during the day and night. This is a picture from the space, the International Space Station. And this shows us something very interesting here. It shows us the height of the atmosphere. So humans and plants and animals are living within that atmosphere. And it is not a very thick atmosphere. It's a very thin atmosphere. So it makes great sense for us not to pollute it and destroy it by the addition of pollutants from burning coal or from basically climatic change by adding carbon dioxide and methane gases that can change the composition of that atmosphere. So if we are fish in a fish tank, the atmosphere is a fish tank. We don't want to pollute the fish tank and get ourselves killed if we are fish in the fish tank. Nuclear energy is foreseen in the future, not just to produce electricity, but along these areas of the world that are not inhabited, along seashores in particular, like in that picture here, we have the oceans, but the ocean have salt water, and nuclear energy, solar energy, in fact, and wind power can be used to desalt that fresh water. In fact, the world has a shortage in freshwater supplies more than it has a shortage of energy. Energy is very abundant, The argument is really just what form of energy society wants us as engineers to extract from it. If they want it extracted from the sun, as engineers, we'll extract it from the sun. From the wind, we'll do it. Hydroelectric power, we'll do it also. And from nuclear energy, we must also be available to do it. So nuclear energy can form the basis of agro-industrial complexes where you produce the energy along a seashore, use the energy to evaporate the seawater. And you know that when you evaporate seawater, you get fresh water, and that fresh water can be used for agricultural land along those arid regions of the world, along the oceans and seas, really the shores of the Mediterranean, for instance, here doesn't have the water here from the Nile, but it has access to the water from the Mediterranean. So a set of nuclear power plants here can turn that desert area into agricultural land. Same along the Red Sea, the Sinai desert, as well as the eastern desert of Egypt in that case, and Saudi Arabia. This is a table that shows the United States energy and electricity consumption. Notice that we are still depending 80% of the total. That's from the Energy Information Administration. You can go to their website and check the newer numbers. Hydrocarbons, coal, oil, natural gas is 80% of our energy use. Nuclear is 8.7, biomass 5, hydroelectricity, wind is still 2%, solar, but solar and wind are increasing. The contribution is increasing at really almost an exponential rate. It's doubling almost every year in general. Okay, I'll let you look at some of those interesting tables here. The Energy Information Agency tells us that in terms of electricity only, not just the general use of energy, but just electricity, natural gas is 35% of our sources of energy to produce electricity. We depend then next on coal. Coal used to be ahead of natural gas 40%. You could see that we are retiring our coal power plants. Now, some other countries are not, like India and China are increasing their energy production. They need more energy to enhance the standard of living of their population. So they're still building large amounts of coal power plants. But natural gas seems to be the leading hydrocarbon, methane, CH4. And in fact, it's a good trend because it reduces the amount of carbon dioxide released to the atmosphere. 20% of the United States electricity is nuclear energy. Remember, it was 8.3 in terms of all the energy sources, but just for electricity, 20% is produced from nuclear energy. And the hope is that the renewables, the wind, biomass, solar, geothermal, may be added together, can reach the same level as nuclear power plant to get a more balanced energy system where we depend on renewables and nuclear energy. So this is a future in the making, and reduce the use of coal and the hydrocarbon sources, because in my view, it's being depleted, as I suggested in general. And in fact, this is the second hurdle that I mentioned earlier that our technological civilization has to overcome, is that we should not destroy ourselves. And we may be the only life form in our, at least, solar system, or, well, we definitely in our solar system, but at least in our galaxy or in our universe. There is no doubt that the annual mean land temperature above and below average has been increasing. And there is no doubt, it may be that it has contributions definitely from other processes that have to do with the rotation of the Earth against the sun, against the activity of the sun, our main star, but the increase in temperature is inexorable, and we have to be able to deal with it. Even countries that are very rich in petroleum are, in that case, already moving by using, of course, they are smart enough to use in the direction of nuclear energy. This is in the United States. The South Texas project has two nuclear power plants, as you could see here, built in a large reserve that shows that nuclear energy can coexist with nature. That's a 22,200 acres nature preserve. Last winter, you remember that they had a problem in Texas with freezing weather. Their power system was not well designed, so they lost one of those nuclear power plants' power generation, and the other one survived and helped Texas get through the problem. However, as I said, other countries in the world, even the petroleum producing countries, this is the in the United Arab Emirates, they have 1, 2, 3, 4 nuclear power plants units in a region that is producing quite a bit of petroleum. So the people there are very far reaching in the future, and they need tremendous amounts of energy to survive in their climatic region. So this is a plant designated as a Barakah plant. Barakah means the plenty or the and they are advanced pressurized water reactors built there by South Korea. I think one of the plants at least, and the second one is coming into production. So it is not an interest in the United States to produce power from nuclear energy, but this is the whole world in general. In what context are we going to use these future nuclear power plants as well as renewable sources of energy? The vision of the future is that it is going to be achieved in terms of what we call the Internet of Things. So the Internet is evolving, and one part of it devoted to the production of energy is what we call the Internet of Things. And based on some analysis in the Der Spiegel magazine from Germany, this is what the conceptualization of that electric future or smart electric grid configuration is going to be. We'll continue in the vision of the electrical production of the future to be still using centralized what's called baseload power generation, and that would be nuclear power stations, because they can be operated with a very high capacity factor, 90%. Hydroelectric power, but hydroelectric power is dependent on the water supply from rain and snow melt. Like in California, the Lake Mead there is losing its water supply. They are into a monumental kind of a drought. Hydroelectric power, though, is used in the American Northwest, like in Oregon and the state of Washington, for hydroelectric power generation. Clean coal, we are going to try to still depend on coal, but cleaning it so that we don't release pollutant to the atmosphere. Geothermal basically are going to be what we call baseload power generation that can operate day and night. But we are going to also think about renewable energy sources. And in that case, we are, in fact, introducing already wind power generation. Like just drive around Champaign-Urbana over a weekend, go northeast to the area of Rantoul and Paxton. Oh, you find wind farms. Go southeast to the area of Philo and Sydney, and you find wind farms. Go to Bloomington, you'll find wind farms. And so basically wind energy is available to a huge extent. Hence, of course, last semester we taught a course on wind energy generation, but also solar, thermal, and solar photovoltaics are going to be introduced and are being introduced. However, because of their intermittence, the sun is not available to us during the night, obviously, or on cloudy days. You'll find that we have to store the energy. So another part of that Internet of Things, let me reduce the size so that we can see the whole thing, you'll find that we have to develop energy storage system. That's why we had our course the last semester on energy storage systems, and we need backups, and the backups are primarily flywheel. You store the energy in pump storage, batteries. Oh, think about car batteries, so Tesla cars and the Volt cars and so on. You can store it in flywheels, turn the energy into hydrogen, and then use the hydrogen in fuel cells. That would be the truck source for the source of energy for trucks in the future, rather than just batteries. And we basically have to store the energy to use it when the sun is not shining or the wind is not blowing. Backup systems depend on using gas turbines in general. So our future is going to be centralized baseload generation, nuclear, hydroelectric, renewable sources, wind, solar, energy storage, different forms, pump storage. You can go on Lake Michigan this summer and to the area of Ludington, southeast Lake Michigan. You'll find that it's hilly, and pumped storage is used there. You pump use electricity that's in surplus to pump water up into a lake above a hilly ground. And then when the demand in Chicago is high, you bring the water down and produce hydroelectric power. So that is all kinds of energy storage phenomena, processes taking shape. Not only is our new energy Internet of Things be composed of centralized base power, renewables, and energy storage and backup systems, but there is a trend also in decentralized power generation. In that case, a farmer that has some acreage of land can build a wind turbine, produce electricity, and have a solar collectors, produce the energy, store it, and use it away from the grid system in general. Now, this is taking shape more or so in Europe. In Germany, most farmers there would put in on their farm, supplement their production of crops by having photovoltaic sources of energy. And it is encouraged there to a great extent, energy that is produced by individuals, like on farms or in areas of land, basically can be connected to the grid system, and they are paid really a tariff, as I call it, that encourages them to do so. Unfortunately, that is not yet the case in the United States. It is being discouraged. So the Europeans are leading the world in that direction. This is a picture of the power production in France. And basically on January the 20th, 2020, at the time of 1730, this was the energy picture in France. You notice that whole part here is nuclear energy. So the French do not have supplies of hydrocarbons, so they depend to a great extent. They had 48,894 megawatt of their electricity produced from nuclear energy. So they depend, as I suggest here, on nuclear energy. They supplement it here with hydroelectric power. You could see 12 megawatt, and they store some of it. So you see here already that Internet of Things is taking shape in countries like Europe. It is not yet implemented in the United States. So our American engineers in our class here know now that they have to catch up on the French and the British and the Germans. They are smaller in size, so they are more dependent on the different sources of energy. So you notice here that they have 180 megawatts of solar energy. Oh, only when the sun is shining. So this is noon. And you notice that it starts maybe at 10 in the morning, and then the solar energy production cannot continue until, or even until sunset, which would be 6 here. It's only during the part of the day where the sun is perpendicular up in the sky. You notice here that in the very early morning here, this part here, the energy is going into storage. That's pumped storage, about 53 megawatts of energy. And that energy is that used back again later on as maybe hydroelectric power. Notice that 48 gigawatt, when you say 1,000 megawatt, that's a gigawatt. So 48,894 is nuclear here, but they use also natural gas. This is that dark part on the top there, hydroelectric power right here. And they still depend on some coal and a very little amount of oil, as you could see. Notice that this graph shows us how the energy need over a daily period changes. This would be midnight, and you continue here over midnight during 6 in the morning. You could see people start going to work, so energy peaks. Then over the day, it comes down a little bit, but then comes back when people get back from work under the condition of no pandemic, obviously, and it peaks again. And basically, in that case, the energy that you stored right here is going to be used later on. Notice that they have a contribution from wind power here, as well as a contribution from solar energy. Very little, but most of the dependence of the French on electricity production is nuclear energy in that case. You can access the site in the main portal in France, where they show you how they manage that. That is basically an Internet of Things. So they have here a control system that manages the different sources of energy. And that shows here as basically the control of the Internet of Things. It decides which nuclear power plants are turned on or off, how to store the energy and extract it back again into the grid. And centralized power stations would be turned on and off according to the supply. In France, the nuclear power plants are by law designed to follow the load, meaning that when there is a demand of electricity, they are designed to start producing the power that is needed. In the United States, that is not the case. And that means that when we design our new generation of nuclear power plants, we have to take that into account, because the nuclear power plants are not going to be there alone, but they'll be accompanied by wind as well as solar. And France is blazing the trail here, showing us what needs to be done in the United States. That does not exist in the United States as of yet in general. So I discuss here the need in the United States to build nuclear power plants that do the load following. If we don't do the load following, then the nuclear power plants should be designed to operate at high temperature for our nuclear engineers in the class. And in that case, when you operate at high temperature, then you can turn water, dissociate water into hydrogen and oxygen, and the hydrogen can be stored and used using fuel cells to produce energy. So you need really the implementation of energy storage. So that is really the challenge for the future of the engineering and scientific profession, both in the European countries as well as in the United States. But the European countries, as I could see here in France, are blazing the trail for us. And we have a challenge here in the United States because our grid system is a hodgepodge of different producers and different suppliers and different transmission companies that are some kind of coordinated by local entities like the MISO kind of power system, but they are not really planned nationwide. For instance, last winter in Texas, we all know that the Texans almost froze but because their grid system, unfortunately, is not connected to the North American grid system, which encompasses the United States and Canada. So if they were connected and they lost one of their nuclear power plants to the freezing events there, what happened to them in terms of their power system collapse may not have happened in general. So there is a description here of the Internet of Things that we need to build in the United States for the future. And I would conjecture of adding that this is really a model for all countries in the world. You have to account for the future use of nuclear energy as well as the future use of energy storage systems in general. The United States is lacking. I would have to admit that. Basically, in terms of the whole world, everybody on our planet has the right to live out of poverty, to have good health, and enjoy life. So this is part of the United Nations General Assembly, the Universal Declaration of Human Rights. Article 25 states, everyone has the right to a standard of living adequate for the health and well-being of himself and of his family, including food, clothing, housing, and medical care, and necessary social services, and the right to security in the event of unemployment, sickness, disability, widowhood, old age, or other lack of livelihood in circumstances beyond his control. This is humanity, and humanity not just for the developed countries, but humanity for all the human race in general. If we look at the global energy use in general, as I suggested earlier, it seems that oil still has been and is the main source of energy. It's a hydrocarbon as well as coal, as well as natural gas. NG is natural gas. These are all depletable, my friend, and they're not going to be there in the future. So that would be a collapse of our technological civilization. These have to be reduced and replaced by the renewables, which are not used enough yet, the hydroelectric power, as well as nuclear, which is a non-carbon source. So non-carbon source and nuclear is our future. In terms of France, since I showed you their Internet of Things, and we noticed that they have a huge dependence on nuclear energy. This is the Palluol, 1, 2, 3, 4 units nuclear power stations in France. That's another 4-unit nuclear power stations. These are cooling towers. That is steam that's used in cooling the reactor. That is not steam that goes through the nuclear reactor. The nuclear reactors are this structure here. 1, 2, 3, and 1/4 would be on this side. So that shows us how the French depend on nuclear energy for their civilization in general. Once we use the fuel from the splitting of uranium, as we'll learn in our class, you'll find that you end up with depleted fuel that needs to be stored in large pools underwater for a few years before it is recycled, and the uranium that is left in them is separated and then fed back into the reactors. In the future, and right now, in fact, we are thinking about when we burn the uranium-235, as we'll learn, we produce other isotopes that are fissile. For instance, if you use uranium-238, the isotope, you can produce plutonium-239. Obviously, you can use it in weapons, but in a better use, you can mix it back with uranium-235 in what's called the mixed oxide and reuse it in producing power. And the amazing, amazing, amazing aspect of nuclear energy in that you can produce more fissile fuel as you are burning the uranium-235. So it's a process of what we call breeding. It is unique in all the energy systems that we have, and we'll learn about this as we go along, in that as you are burning the fuel, you are producing, if you design the system appropriately, more fuel than what you have consumed. So in fact, we have access in terms of knowledge of an infinite supply of energy that we have to use in our future. You can use another isotope that exists in nature, the thorium. From thorium-232, we learned how that can be done. You can absorb a neutron in it and produce another material, uranium-233, that is fissile, that you can use to produce energy too. And you can produce more energy, more fissile, more fuel to produce energy than the fuel that you are consuming. And that is unique in nature. So this was the promise of fission energy, the process of breeding. The promise of fusion so far can be a combination of fission and fusion. So in that case, we can use breeding, but we have also an unlimited supply of deuterium as a fuel in our oceans in general. This graph again shows us the United States energy consumption. You notice that its total dependence on petroleum, natural gas, and coal, 8% renewable energy, and nuclear energy about 9%. So the future is going to be these hydrocarbon sources depleting, and the increase is going to be in the renewable energy, solar, geothermal, biomass, wind, biofuels, wood, and hydropower, as well as it's inevitable that we have to proceed in the direction of renewables and nuclear energy in general. This is the cost. It's not just a need for environmental reasons, but it's also a matter of economics. And you could see here that solar thermal, where you boil, say, a working fluid and take it to a turbine to produce electricity, and solar photovoltaics, where you have solar collectors, they're still expensive energy. But when you go to wind and you go to nuclear, where is the nuclear here? Advanced nuclear, the costs are much, much less. So the trend really is a direction of wind and advanced nuclear, which we haven't built yet in the United States. We are still dependent on 40-year-old plants. Nuclear, again, has a great advantage in existing plants of having a very high capacity factor. 90% of the time, you can get power from nuclear power plants. Coal power plants, for instance, would stop operating on days where the weather is very cold. So a nuclear power plant is refueled only once every year and a half, whereas a coal power plant needs every day a train of 100 cars to be brought to burn for the same amount of power. The coal power plants also have a high capacity factor, but they cannot compete with the capacity factor of nuclear power plants. Here in Champaign-Urbana, the electric utility that serves us is a utility from Missouri. In fact, it's not an Illinois utility. It's a utility from Missouri, Ameren, Illinois. They have their subsidiary, but you could see that they depend on the electricity that we are using right now. 48% is from coal, 23% natural gas, and 16% from nuclear energy. In fact, in spite of the fact that we have a nuclear power plant 45 miles away from us here. Globally, over the whole world, the trend in terms of adoption of nuclear energy is definitely very large. China is suffering from pollution in its large cities and pollution from the burning in coals. Locally, people burn coal inside their homes and then end up with a great level of health pollution. So China is moving in the direction of renewables, building wind farms, as well as solar energy plants, as well as nuclear energy. So this is the expected growth in different parts of the world in up to 2035 in gigawatts. This is the power of different nuclear installation in general. The black shows the existing capacity, and this one here is the planned capacity. So it's not just the United Arab Emirates, but most of the industrialized nations. You notice that the concentration of existing nuclear power plants are only in the industrialized countries here. This is the United States, the Europe, as well as Japan. They turned off their nuclear power plants for safety considerations, redesigned for safety after the Fukushima accident, and but they are coming back to it because they cannot depend on expensive natural gas, even though in Europe, Germany depends on natural gas exported to it from Russia and some of the countries in Central Asia. Coming back to the United States, you notice that the largest production of nuclear electricity happens here in the United States, followed by France, Japan, Russia, South Korea, Germany, Canada, Ukraine, China, and then Spain. In the United States, many of our nuclear power plants have been operating for a long time already, about 40 years, getting into the 60 years region. Notice they're concentrated in the Southeast. The Southeast cannot depend on wind power because their wind power resources are very limited, but you find nuclear power plants in the United States, in the Midwest, some on the West Coast. They're not very well spread there because of the fact that it's a highly seismic region. They worry about earthquakes. But notice here the northeast of the United States, these are all units of nuclear power plants. In the United States, you'll find that we have only 2 nuclear power plants right now under construction. There are 19 reactors proposed, 11 planned, and there is a trend towards small units because of the lack of capital, the capital destruction of the economics the economic destruction of capital in 2018. We are still suffering from it. So utilities are moving towards many nuclear power plants in general. Definitely nuclear power plants would be contributing to the reduction of carbon emissions in general. So you could see here per megawatt hours of energy. This is our utility, Ameren, Illinois. You could see that they measure the carbon dioxide emissions, 1,372 pounds per unit of energy produced. This is mega, million watts, that's power, multiplied into time. Power by time is energy. So if by million joules of energy, they are releasing 1,372 pounds of carbon dioxide. But not only carbon dioxide, they release also what's called the NOxes and the SOxes in the utility business. X here stands for NO1, which is nitrogen oxide, and NO2, nitrogen dioxide. The same for SO, sulfur monoxide, and sulfur dioxide. Those 2 gases, or 4 gases, may be released to the atmosphere, turns into nitric acid and sulfuric acid. And this destroys really the lakes and leads to acid rain. And if they get into the lungs of people, they cause disease in general. Very little nuclear waste is being produced. The uranium that you mine from the ground ends up as fission products. In the same way that you mine it from the ground, you go and put it back into the whatever is left from the burning of uranium back into the ground. Basically nuclear reactors, the pressurized water reactors, produce waste, but that waste doesn't remain as waste forever. Remember that uranium is existing in the Earth's crust with a half-life. It has been radioactive since the Earth was created 6.4 billion years ago in a large explosion of a star, supernova, and it has been radioactive and will remain radioactive forever. When we burn it in nuclear power plants, in fact, we reduce the radioactivity of the uranium in the fission products, and they have to be stored back into the ground. If we use a thermal uranium cycle, another isotope that we can use for fission, the amount of dose of radiation even decreases over time. So we are contributing to the reduction of radioactivity in the environment by burning it in nuclear power plants in that case. Definitely, some very interesting aspect of nuclear energy production is that it has a symbiotic effect with the other renewable sources. So when we were able to take this class for a field trip, we visited that wind farm here at Vincennes in Illinois here, Marseille actually, Illinois. And this wind farm here and here is called the Grand Ridge Wind Farm. and it's operated by a company called Energy. And notice something interesting here is that it is right next to the LaSalle nuclear power plants. And the amazing thing is that the nuclear power plants were built by the General Electric company, but the wind turbines were also built by the General Electric company. And you could see here how they can coexist together. On that side here, you have the summer cornfields, and the wind power generation occurs there while the fields are being planted. And this is during the winter. The wind turbines are rotating, and the nuclear power plant is producing the energy produced by the same company. This is a company that you have to interview with if you have interest in nuclear energy. General Electric. In Europe, it would be the Siemens company in Germany. The production of electricity is becoming more important, and we want to avoid coal. We want to replace coal by renewables and nuclear energy because of the advent of new technology in transportation. This is plug-in electric cars, Teslas, and so on. You have to recharge the batteries. That takes really 12 hours maybe to recharge, and that be overnight. So electricity would be the way to really produce our future our future transportation system, not just industrial use in general. Unfortunately, the United States is lacking in terms of new reactors. That are only 2 units under construction in the United States. Some new companies are trying to put into the place in the market small units, but 2 units, this is what we are going to be calling the pressurized water reactor. It's an advanced passive 1,000 megawatt electric built by Toshiba in Japan and Westinghouse in the United States. Westinghouse has been purchased by Toshiba, so it's really the construction and the design is a safe design, but it's 2 units, Vogtle Unit 3 and 4, and they are being built right now in Georgia. This shows us the site, and it shows us it's a huge industrial kind of facility. This is the bottom of the pressure, the containment structure for the PWR, 900 tons being carried by those huge cranes. So the United States is moving in the direction of nuclear power generation. The electrical generation in terms of plants in the United States, according to the Energy Information Administration, you could see here that wind is being increased by 22% in terms of plants, solar photovoltaics by 11%, natural gas is 67%. So there is a dependence in the production of electricity on natural gas. And in fact, it is with wind power, they're both competing with nuclear energy production. Now, why is it that I should be taking courses in energy production? This is a good reason for it. You'll notice here that as the date here starts in 2018, where we had basically almost what people call the Great Recession. And you notice that different levels of education affected really the future of people. Starting from that time, you notice that people who had people with high school diplomas only, definitely their employment decreased by 6%. And after the time on the recovery, well, it remained at 6%. They didn't find their jobs back. People with associate's degree of some college education, they lost their jobs and they recovered it. But the job market basically has been different for those here that had people with a bachelor's degree or better. In fact, in that case, they took the slack, even though it's not in the same magnitude or number of those who lost their jobs permanently. You'll find there is a higher demand for people with advanced degrees, so that what you are working on as a bachelor's, maybe you'll go for a master's or some PhD is almost necessary for your future in general. In the workforce, you find that there is a huge emphasis now in new jobs on women. Women are taking part in the economical aspects of the recovery since 2018. And the reason that the competition is much harsher is it is only available for people who are learning high skills. And because of the automation in the industrial system. So this is robots assembling a car, and it is not humans putting the car together anymore. So acquiring high skills and knowledge is almost a necessity for surviving in a modern society. And this is the first chapter here on the preface, a general description of the situation of the job market in general. I'll stop sharing and maybe look at the chat room for any questions here. Okay, let me go back and try to answer some questions, but then I'll come back and try to cover the next chapter. We have to cover 2 chapters maybe every time. I answered this question before. What does it mean by rejected energy? Rejected energy is associated with the efficiency of the process of producing energy. We'll cover that in a chapter by itself. And you'll find that the environment is, I'm answering the question by Mohammed Al-Jichi. The environment is full of energy. We have it in the sun, in the wind, in nuclear, hydroelectric power, and so on. And the way to extract the energy from the environment is that you must have or establish a flow system. For instance, if you want to produce hydroelectric power, you go to a natural system, maybe Niagara Falls, and you place a turbine there that extracts some energy from the, of course, energy in the waterfall at Niagara Falls. But what if you don't have a natural source of energy like the Niagara Falls? So what do? We build a dam. We store the energy behind the dam, and then we extract that energy by placing turbines to get the potential energy back into kinetic energy and then into electrical energy. So in that case, you need a flow system. But to establish the flow system, you need some machine, either a wind turbine to extract the energy from the air, or a water turbine to extract the energy in the hydroelectric power plant. As you rotate the machinery, definitely you are using, in that case, generating turbulence in the water. And you'll find that in the process, the energy that you stored is not equal to the energy that you can extract. And the difference between the two is energy that is basically unusable. It is not really rejected by choice, but it is the energy that we have to place in the flow system. Because if you have water flowing, it has kinetic energy of half mv squared, and you can extract only part of it. If you have the wind blowing, it has kinetic energy, but you can only extract part of it. And this is described in thermal system by the ideal Carnot cycle efficiency, and in aerodynamic system like wind energy production by what's called the Betz equation in general. From Anchal, our TA answered you in a different way. She suggests that reject energy is the energy which is not utilized to do useful work, or say the energy which is wasted. It is not really wasted in a way, but it is energy necessary to establish a flow. And without the flow, we cannot extract energy. Think about gasoline in your tank, in your car. If it's stored in the gas tank, it's stored energy. But when you start burning it, rotate the machinery in your car, the engine, you have a flow system. And you have to basically expand part of that energy that you have available in any form, whether it's thermal or hydrodynamic or aerodynamic, to establish the flow. Of course, we can extract more of the energy by better designs of wind turbines, by better designs of water turbines, by better design of solar collectors, and so on. I hope that answers the question in a slightly different way. is waste heat rejected energy? Waste heat is, I like to, yeah, Mohammed Al-Jichi again. I like to more think about it as energy that is necessary for the extraction process. If you want to produce thermal energy, you need a high temperature reservoir, something very hot, and then a low temperature reservoir, something very cold, and you let the energy flow from the high temperature reservoir to the low energy reservoir. And that flow itself is needed to be able to extract part of that energy that's available to you. And in thermal processes, in nuclear power plants, for instance, you'll find that you can extract only 30% of the energy. Remember the Sankey diagram that I've shown you? The useful energy we get from our primary energy supplies is maybe 32 Qs, whereas the energy supply itself is 100. So only the efficiency is 32. So people like to call it rejected energy, but it's not rejected really. It's energy that's needed to have a flow process. And without a flow process, as I'll show you later, you cannot extract energy. Think about it this way. So it is not totally lost. It goes back to the environment, and it is necessary to get a flow system. Without a flow system, energy just remains unused. It remains stored in general. Don't we usually build dams in places where water flows a lot from the rain so that we don't have to use machine that flows the water back up, inefficient to transfer energy from converting potential energy into kinetic energy and back into potential energy? The answer to this, yes, you don't need to store the energy, but if you have, say, energy, like in Europe, they have energy available from the wind, maybe in Spain, and maybe it's at night. So the wind is blowing, the wind turbines are rotating, they're producing electricity. Instead of simply not using it and having it wasted, they use the electricity to pump the water up to an artificial lake. And in that case, the wind energy, which is aerodynamic or fluid energy, if you want to call it, it becomes potential energy. Then you can extract it back as when there is a high demand for electricity, early in the morning, for instance, when people are getting to jobs, industries are started, you get it back. But in the process, you are losing part of it in friction, maybe in the piping, in turbulence in the water that heats the water. So in that case, it's a process of using energy that otherwise is being wasted. And in fact, it is not just important for renewables for us to store the energy when the wind is blowing or the sun is shining, for periods where the sun is not shining or the wind is not blowing, but even in the production of conventional sources like nuclear energy, it is inefficient to shut down the nuclear power plants when there isn't much demand for it, the wind is blowing. So in that case, the nuclear power plants continues operating, producing energy that is wasted. And think of it this way. We are sitting right now using our computer, we have lights in our homes, and basically the utilities that are selling the electricity are providing us with a service in that if you turn on a switch, you get the electricity that you need. But what if you don't use that electricity? That electricity is wasted, and it's better and increasing the efficiency of the system to provide ways of storing that energy that is wasted instead of store it for some other time where we need it. Even though in the process of storage, there is friction. Say if you use a flywheel, the flywheel is rotating, there is some friction. So some energy is lost to friction. So every energy conversion process is associated with some amount of energy used to maintain the flow in the process. It is not wasted energy because it's necessary to keep the process going. And if we don't keep the process going, we cannot extract the energy. Fatima Al-Ghanem, did I answer your question here? I hope you read some of the material, and then later on, I'll describe the conditions by which we can extract energy from the environment. Yeah, thank you too. We have a few minutes left, so if you have questions, please pose the questions. Now I invite you, I'll go to screen sharing. First, our first chapter really was some kind of an overview of nuclear energy, and I put a new sign there. The next chapter I'll cover is the first introduction of nuclear energy, the birth of the nuclear age. Once we cover that chapter, I'll put a new sign here. And as we proceed with different chapters, the new sign means that this is a chapter that you are supposed to read. After you read it, please, you go to our to the website there. I'll show you. You read the list of assignments, either in the Word format or the PDF format. You answer the question. You have 1 week to submit the answer. I'll add to this here more material because we covered more material than just material in the Kardashev scale. You have 1 week to submit it to the Compass 2G website. You go to https Compass 2G. Our wonderful TA will receive your assignment and you'll get a grade for it. And by the end of semester, 40% of the grade goes to the assignments and 60% goes to the tests that we are going to have along the semester. I hope that is clear. And I'll go back since we have only 5 minutes to go here very quickly. If there are no questions, I want to use all the time available to us to cover the next, start covering the next chapter. If I don't see any questions, I'll use those few minutes to start about the first reactor or the birth of the nuclear age. This is a historical kind of perspective, how the nuclear age started. The interesting thing is that the nuclear age started here in Illinois, where we are, well, if you are at the university and you'll be there maybe hopefully next fall, it started in Chicago. And in Chicago, they have basically at the University of Chicago is squash courts and in what's called the Stagg Field. And at that place in Chicago, there was an experiment that was built. And we don't have pictures, photographs of the experiment when it happened, but a painter painted it as to commemorate the event. And what you could see here is literally a pile. And that pile was a pile made out of graphite. Graphite is really what we use every day if we use a pencil. When you use what's called the lead pencil, it is not lead, it's graphite. And graphite is a form of carbon. So the isotope in that case is 6-carbon-12. And those blocks of graphite contained balls made out of uranium. And the configuration, as I'll show you in a moment here, let me see if I can show you the configuration right away before we get into more details on it. Let me see. No. We have a picture of it. Here is actually a picture that was taken of that pile. So you could see here that's a 10th layer of the pile, little blocks of graphite with balls of uranium placed in them. And they were adding one layer upon the other, upon the other, upon the other, until they reached what is called the critical mass. And the scientist in charge in that case was Enrico Fermi. And Enrico Fermi is shown right here. He was a real genius. He came in from Italy, from the University of Bologna at the beginning of the Second World War. He adhered to the Catholic faith, but his wife was Jewish. And because of that situation and the basically Nazism and fascism emerging in Europe, Nazism in Germany persecuting their Jews, and fascism in Italy also persecuting both Catholics and Jews, that he found his way to the United States and became the leader in that project of building that Chicago pile #1. He's shown right here. The fascinating thing is that they were adding layer upon layer of this mixture of a moderator, as we are going to call it, graphite and uranium, that is the fuel. And we'll come back to that picture later on. And this event happened on December 2nd, 1942. And at that point, they were reaching what we are going to call a critical mass by adding a layer upon layer of the uranium mixed with the graphite. And this is interesting enough, the way that all nuclear reactors operate today, except that graphite as a moderator is replaced by water or heavy water or beryllium, and the uranium is the same uranium, except that for water we have to enrich it in the isotope uranium-235. And at that point in the history, Enrico Fermi sent a coded message to people who were overseeing him from Washington, D.C. The message was, you will be interested to know that the Italian navigator, Italian in that case referred to Enrico Fermi, who was Italian, and but they suggest, of course, Columbus has just landed in the New World, and the natives were friendly. So that was the success message about the first ever production of a chain reaction, and humanity has learned it here in our state of Illinois in 1942. And the rest is history. And we'd like to combine the learning of the history of what happened and to be able to understand the present and also look into the future. I'll stop here for now. And again, I'll be available for the rest of the afternoon if necessary to answer questions in the chat room.